Yes, so Srikal students, let's derive equation of continuity and understand it. Let's imagine a pipe with varying cross-sectional area. The area at 1 is A1, and let's say the velocity is V1. The area at point 2 is A2, velocity V2, or you can even say the speed is V2. Now, students, if you just see, if you just take a imaginary plane perpendicular to the direction of fluid velocity at point A and even at point B also, imagine that the fluid is steady, that is, the velocity is a function of location, but the velocity is not a function of time. Okay, there are fluid particles crossing this plane, and there are fluid particles crossing this plane also. Now, imagine that the fluid is incompressible. What does that mean? The density of the fluid is not changing, right? The density is remaining same throughout the fluid flow. Okay. If density is same throughout the fluid flow and the flow is steady, obviously we can understand that the fluid particles crossing this cross section at any instant, the fluid particles crossing a second imaginary plane perpendicular to the direction of fluid flow and this plane at any second, at any instant would be same. In other words, we can say the mass flow rate m dot, mass flow rate of the fluid would be same at all the three cross section. All right. Now in time delta t, maybe in 1 minute, maybe in 4 minutes or 5 minutes or 10 seconds or 1 hour, let's see how much mass of the fluid flows in delta t. So that would be mass flow rate into time, right? Mass flow rate is kg by second into time, that is second. That would be equal to, this is the mass flowing, and kg by second is the mass flow rate. How would you get that? Well, we have volume flow rate. Volume flow rate is meter cube divided by second. The fluid discharge can be expressed either as mass flow rate or volume flow rate. How we will get volume flow rate? Volume flow rate would be A1 into V1, right? The unit of this is meter cube by second. If I multiply this with rho, that is density, the unit of density is kilogram per meter cube. You see, meter cube cancels with meter cube. Ultimately, what I get is kilogram per second. So, volume flow rate into density will give you mass flow rate. Remember that. So, see that students. Now, volume flow rate here is rho A1 V1. This is volume flow rate. And volume flow rate at 2 is rho A2 V2, right? Now students, what is the mass which has flown, which has flowed uh, this cross section L time delta t? If I multiply this by delta t, What is the mass of fluid which has flowed out in time delta t from this cross section? That would be multiplied by delta t, already explained here. So see that, students, delta t cancels with delta t, rho cancels with rho. So what I get is A1 into V1 is equal to A2 into V2. This equation is really very important in the derivation of Euler's equation or Bernoulli's equation. Very, very important equations to understand fluid dynamics. Students, on a close look, you would understand that if A1 is bigger, let's say, as in this case also, A1 is bigger than A2. A1 is bigger than A2. So, but the product of A1 V1 is equal to A2 V2. Well, that means A1 is bigger, A2 is smaller. Obviously, to make the product constant, V1 has to be smaller and V2 has to be greater. Well, this is a great observation. We understand that when the fluid is flowing downstream, when the fluid is flowing like this, and here the area of cross section is less as compared to this area, we can quickly make a judgment from continuity equation that the velocity here would be quite large as compared to the velocity here. You can replace this word velocity with the speed also. Reason behind, the fluid is changing directions. Okay, it doesn't matter. Don't get confused in the concept of velocity and speed. So, other way, if the fluid is flowing in a converging section, so here whatever is the velocity, when the fluid comes here, the velocity of the fluid as a whole, as a continuum, here would be less. To make the volume flow rate or the mass flow rate of the fluid at both the cross sections constant. So remember, in a steady flow, whether it's a pipe of same cross section area, it's a diverging pipe, or it's a converging pipe, you know, the equation of continuity holds good, giving us an understanding of when the area is changing, how the velocity is changing. Students, see here, when the fluid is flowing in this direction, it is diverging area. When the fluid is flowing in this direction, it is converging area. Converging area. Thank you very much. Based upon this, watch for the next video, that is derivation of Euler equation, or, and then hence Bernoulli equation. Thank you.